So we're going to look at some theorems, the Rolle's theorem and mean value theorem. And in order to be able to use these theorems, certain conditions have to hold. So let's just read through it and then talk about it. So it says, Rolle's theorem, suppose y equals f of x is a continuous over a closed interval AB. Okay, so it has to be, again, a closed interval, and it has to be a continuous function. So we got continuous, and we got a closed interval. And it's differentiable at every point of its interior on AB. Okay, so here we have some other information that it has to be differentiable on that open interval AB. So no sharp corners, no jumps in our graph. If f of a equals b, so those are end values of our interval that we're looking at. So those y values have to be the same. Then it tells me there has to be at least one number c in that open interval AB such that that derivative equals 0. Okay, so a couple things could be happening here, but to me, this really makes sense, right? If you have some x value a here and x value b here, and our y values are the same, in order to draw any graph that's continuous in between a and b, and to get back to this value, I'd have to be able to turn around and turn back over there. I mean, I could, if I wanted to, A, here's B, could go below the x-axis, right? But here, my derivative is 0. It's possible it turns more than once though. So notice here, here's another graph where your y value at x equals a and x equals b are the same, but there's multiple places in here where the derivative at that value is 0. So in this case, there's 3 different places where our derivative is 0. But this says there's at least one number c where our derivative equals 0. It's also possible these were the same y values. It's just a horizontal line between a and b. Then any value between a and b would give us that derivative was equal to 0. Okay, so that's Rolle's theorem and what that says. The next theorem is the mean value theorem. So the mean value theorem, we also have to have a function that is continuous over some closed interval at AB. So same conditions hold as it was for the Rolle's theorem. Also has to be differentiable on some interval, open interval AB. So no sharp corners again, no jumps in the graph. Well, I guess if it wouldn't be continuous if there was a jump. Then there's at least one point C in that interval from AB such that the slope of the secant line, this is just the slope between x equals a and x equals b, has to equal the slope of some interior value. So slope of the tangent line, there's some x equals c where the slope of the tangent line at x equals c is the same as the slope of that secant line. So looking at how this could look like pictorially, graphically. So in this theorem, those endpoints A and B don't have to be the same y value, like Rolle's theorem said it did. So if we look at the value here, when x equals a, our y value here is f of a, x equals b, our y value here is f of b. I'm looking at the slope, so the change in y all over my change in x. This slope right here, there's some value in between a and b that has the same slope. And in this case, they show us where it is. If you look at x equals c, and we drew the tangent line through x equals c, you notice that those are parallel lines. Remember, parallel lines have the same slope. Okay, so that's the mean value theorem. So let's look at some examples using the mean value theorem. Okay, so the example says f of x is equal to x cubed minus x squared. We're on some closed interval, -1, 2, and we want to find all values or values of c that will satisfy the mean value theorem, meaning that the derivative, there's some derivative f prime of c that would give us the slope of the secant line between -1, x equals -1, and x equals 2. So we need to figure out what those points are. And so we need to look at what is f of -1. So going back into our original function and plugging in -1 wherever we see an x. So -1 cubed minus -1 squared. -1 cubed, that's just -1, minus -1 quantity squared, that's +1. So I have -1 minus 1, which is -2. Okay, so I have a point I know when x is -1, my y value is -2. So I also need to see what's happening when x is 2. So I need to find that point. So I'm looking at f of 2. So go back into our equation and plug in 2 wherever you see an x. So we have 2 cubed minus 2 squared. Well, 2 cubed, that gives me +8, minus 2 squared, that gives me 4. So 8 minus 4 gives me 4. So I have a point here at 2, 4. So I want to find the slope between these 2 points. And so looking at the change in y, so 4 minus -2 all over 2 minus -1. So let's simplify this down. So we get 4 minus -2, 4 plus 2 is 6, all over 2 minus -1, 2 plus 1, which is 3. So we have a slope of 2. So this is telling me then I need to find some x equals c such that f prime of c is equal to the slope of that secant line, which in our case is 2. Okay, so here we have what we need to find. And so we need to first find the derivative. So let's find f prime of x. So that's not too bad with the equation we're given. So the derivative of x cubed, that gives us 3x squared, minus the derivative of x squared, which is 2x. So we're looking at when is this 3x squared minus 2x equal to. So we need to solve this equation to figure out what our value c is. So you have to look at what type of equation you have. Notice this is a quadratic, so we want to set this equal to 0. So 3x squared minus 2x, subtracting 2 on both sides, so minus 2 equals 0. I want to factor this if possible. That's probably the fastest way. Let me see. So I have 3 times -2 is -6. Are there two numbers that multiply to -6 and add to my middle term -2? Actually, I don't see any numbers that would work. 2 and 3 don't work. 1 and 6 don't work. So it actually is not factorable over the rational numbers. So we need to use the quadratic formula. So I get x is equal to -b. So +2 plus or minus the square root of -2 quantity squared. So 4 minus a, which is 3. Oops, minus 4ac. So minus 4 times a, which is 3, times c, which is -2. All over 2a. So 2 times 3, which is 6. So we have 2 plus or minus the square root of 4. I'm multiplying two negatives, so this is plus. So 4 times 3 is 12, plus times 2 is 24, all over 6. So I get x is equal to 2 plus or minus the square root of 28 all over 6. So square root of 28, that's 4 times 7. So we can pull out the square root of 4, which is 2. So 2 root 7 all over 6. Think of it as factoring out a 2 and then canceling it with a factor of 2 in the denominator. So 2 goes into 6 3 times. So we got our value. There's two different values that would give us a slope of +2. That is when x is 1 plus root 7 all over 3 and 1 minus root 7 all over 3. We need to be careful because it has to be between x equals -1 and -2. And so when we're looking at that, we need a calculator to see if we can figure that out. If any of those, at least one of those has to fall in that interval by our theorem. So let me pull out the calculator. Okay, so I just plugged our values into the calculator. So x plus root 7 all over 3 is 1.22, which falls in between -1 and 2. And we got x was approximately -0.55, which is also in the x values between -1 and 2. So there's two values of x equals c, and if they wanted the exact value, then you would keep it with the radicals in there and not simplify it down. But there's two c values which give us the derivative at those values equal to the slope of the secant line at those two n values. Okay, so looking at another example, we're given that f of x is equal to x raised to the 2/3 power. We're given a closed interval from -1 to 8. So we will need to make sure, and it's asking which of the functions, or does this function satisfy the hypothesis of the mean value theorem on the given interval, and which do not give reasons for your answer. So we need to show that this is a continuous function on -1 to 8. Let's see what the other rules were. It has to be differentiable between -1 and 8. So if I look at this, and maybe it would help me if I looked at this as a radical instead of the rational exponent. This is the same thing as f of x is equal to, well, that 2/3 power, the root I'm taking is a cubed root, and then I'm squaring my x. Or if it helps me, I can write it as the cubed root of x quantity squared. So if I look at this, I notice that because it's a cubed root, I don't have to worry about having positive or negatives underneath that radical. I normally want positives under there, but I need, because this is an odd index, I know that this is continuous everywhere. So it's continuous, it's defined. It's continuous and defined on our interval, closed interval, -1, 8. So now let's look at the derivative and make sure that the derivative is defined everywhere so that it's differentiable, showing that it's differentiable. So if we look at the derivative of f of x, I'm going to keep it in this exponential form when I take the derivative. So let's bring down our power, 2/3 x, and subtract 1 from our power. So 2/3 minus 3/3 is -1/3. And so this is equal to 2 all over 3. And then we can bring this exponent down to make this positive. So the cubed root of x in the denominator. So we have a problem in here. This is undefined. When x is equal to 0, I can't have 0 in the denominator. And so if I look at that, notice that that is contained in that interval from -1 to 8. So at x equals 0, it's undefined. And that means it's not differentiable. At x equals 0. And 0 is contained in that closed interval that we are looking at. And so because of this, this condition doesn't hold. So this condition makes it so we can't use that mean value theorem. So we cannot use the mean value theorem. If you looked at the graph of that, you're going to have a sharp corner there when at x equals 0, when you graph f of x equals x raised to the 2/3 power. So if you graphed that original function, f of x equals x raised to the 2/3 power, notice that it is continuous everywhere, but we have this sharp corner here, so it's not differentiable. The derivative on the left would be different than the derivative on the right. So it's not differentiable there, and that, again, mean value theorem didn't hold. Okay, so there's 2 corollaries in this section that talked about the Rolle's theorem and the mean value theorem. Corollaries, they're kind of like theorems. They have been proven and hold true. They just aren't as strong. But in here, corollary 1 states that if we have that the derivative is equal to 0 at each point x on some open interval AB, then our function has to equal a constant c for all x contained in AB. C is that constant. So basically, all you have is a horizontal line. So if we found that the derivative was 0 anywhere between AB, this has to be a horizontal line. And that horizontal line just happens to be C. Okay, so that makes sense. The next corollary says if f prime of x is equal to g prime of x, so the derivative of one function is equal to the derivative of another function at each point x on some open interval AB, then there exists some constant c such that f of x is equal to the function g of x plus some constant for all x contained in AB. That is, if we took the function f of x and subtracted off the function g of x, that would equal that constant on AB. Basically, all it's saying is we're taking some function f of x. So maybe this is our graph of f of x. In order to get the derivative to be the same anywhere on this, well, it could be the same function, and that constant would be 0. Or we can shift this up. So we're just adding some constant to this. So if I added some constant here, notice that it would be the same shape. It would just be shifted up, in this case, c units. So this would be g of x, which in this case, let's say is f of x plus c outside the function. Or I could subtract some number. So if I subtracted off some number from f of x and I graphed it, just shifting that graph. So anywhere that I chose a point on the graph, we would have the same slope. Oops, and mine's a little off, but you can get the idea. So that's what that corollary is stating. Okay, so here we're given the derivative function. So we're given the derivative is equal to 2x minus 1. And we want to find the function with a given derivative whose original function passes through the point, in this case, 0, 0. So we need to think backwards. And this, I think, is preparing us for when we jump into finding integrals, the antiderivative of a function. So we have to think backwards. What would give us, right in here, what would give us when we took the derivative 2x? Well, if I think about bringing down the power and subtracting 1, I notice that x squared, if I took the derivative of that, I would get back 2x. Now, kind of thinking backwards again, minus, what would I take the derivative of? That would just give me back a 1. Well, I know I could take the derivative of just x and get back 1. The problem is that I can have any constant in here plus c, right? Because if I took the derivative of any constant c, that would be equal to 0. So I'd have like a plus 0 here, and we just wouldn't write it. So now we want to satisfy this condition. So this is saying when x equals 0, y is equal to 0, right? Or f of 0 is 0. And so let's look at that. Let's plug in 0 wherever we see an x. And let's plug in 0 for f of 0. So looking at that, we get 0 is equal to 0 squared minus 0 plus c. Just plugging in my x value and my y value and then solving for c. So in this case, 0 is equal to c. So c is 0. So the function, original function that would hold, that would give me this derivative and has a point 0, 0 on the original function would be just f of x is x squared minus x. So let's look at another one. What if we're given that our original function, or not our original, our derivative function, and this time they call it g prime of x, is equal to 1 over x squared plus 2x. And a point, negative 1, 1 is on g of x. So we want to look at what is our original function. So maybe it might help us, maybe not. We've got to think about backwards. What would give us a 2 down here? Well, let's look at this as bringing this up, x to the negative 2 plus 2x. So if I subtracted 1 from my power, after I took the derivative, I would get negative 2. So to me, you can always look at it and make sure. X to the negative 1, that would, if I subtracted, if I bring this down, I get negative x to the negative 2 power. But I want it to be positive out here in front. So maybe if I have a negative x to the negative 1 power, so let's just test it. If I bring my power down front, negative times that negative is positive 1, and subtract 1 from my power, that would give me this 1 over x squared. Plus, and so thinking again, what derivative gave us 2x? Well, derivative of x squared is 2x. And then we have to add some constant c here, because we know that taking the derivative of the constant would have just gone to 0. So if we could add any constant to get back this derivative. So let's just rewrite it a little bit. So g of x is equal to 1 or negative 1 over x plus x squared plus c. So we want to figure out what c is. And we're given a point. We're given when x equals negative 1. We're given that g of negative 1. That y value we get back is positive 1. So when y is 1, this is equal to negative 1 over x, which is negative 1, plus x, which we're plugging in negative 1, plus c. So we get 1 is equal to negative 1 divided by negative 1 is positive 1, plus negative 1 quantity squared is positive 1 plus c. So 1 is equal to 2 plus c. Subtract 2 on both sides, we get what c is. C is negative 1. So the original function that would have that point, we have to plug in negative 1 for our c value. So that original function is g of x would be negative 1 all over x plus x squared minus 1. So we'll get into this more in a few weeks where we look at antiderivatives. This is, again, I think is trying to get you prepared for what's coming up. So tomorrow we'll look at finding intervals where a function is increasing and decreasing by looking at the first derivative, being able to find max and mins, local max and mins off of the first derivative test.